In this video, we want to find Maxwell's electromagnetic field equations written in covariant form. Let's start from phi nu. We define phi nu as the components of a covariant vector, which is the electromagnetic potential vector. And from phi nu, we can form an antisymmetric tensor that Einstein called f rho sigma, which is also called a 6 vector, as we know, by taking its curl. So by taking the curl of phi nu, we define f rho sigma. And in particular, f rho sigma is defined as, we know that the curl written in covariant form can be written like this: derivative of phi rho with respect to x sigma minus derivative phi sigma with respect to x rho. Now, in another course, or in general, the usual notation for phi rho or phi sigma is with the letter A instead of phi. That's the 4 vector of the potential. That's how it's usually written. It's written as A rho, A sigma, A mu, whatever you want for the index, but the letter used is the letter A, not phi. In this case, Einstein uses the letter phi. It's just notation. Now, we also know from tensor calculus that we can write down this relation, d f rho sigma with respect to x tau, and then we add similar terms where the indices rho sigma and tau are permuted. So we make a permutation of those indices. We have df sigma tau with respect to x rho plus df tau rho with respect to x sigma, and this is equal to 0, as we know. This tensor equation here contains only 4 scalar equations, and if you write these equations down, you get something like this. We have a system of 4 equations: df23 with respect to x4 plus df34 with respect to x2 plus df42 with respect to x3 equal to 0, and then you have df34 with respect to x1 plus df41 with respect to x3 plus df13 with respect to x4 equal to 0. Then we have another one. Let me also try to write more clearly that this is the index 1. The third equation is df41 with respect to x2 plus df12 with respect to x4 plus df24 with respect to x1 equal to 0. Then you have one last equation here, df12 with respect to x3 plus df23 with respect to x1 plus df31 with respect to x2 equal to 0. Now, these equations correspond to one pair of Maxwell's equations, and in particular, we can show that if we choose the following 6 independent components of the tensor f sigma rho. So we have to choose f23 equal to hx, the x component of the magnetic field. Also, let me tell you that I will consider a system of units where the speed of light is equal to 1, so we get rid of some constants. f23 is equal to hx, f31 is equal to hy f12 is equal to hz f14 is equal to ex, the x component of the electric field, f24 is equal to ey, f34 equal to ez. Now these are the 6 independent components of the tensor f sigma rho, and the other components of course can be obtained from the fact that this tensor is antisymmetric. And if we choose these components, we can show that, as I said, these 4 equations here correspond to one pair of Maxwell's equations. In particular, let's just consider, for example, the first one. This first one becomes, with this definition, dhx with respect to x4 plus dez with respect to x2 minus dey with respect to x3 equal to 0. But this can also be written like this. It is minus dhx with respect to x4 equal to the curl of the electric field, and in particular its x component. So with this definition, you can find that these equations can be written like this. If we use the usual three-dimensional vectors, we have minus the vector h with respect to time equal to the curl of the electric field, and also the divergence of the vector h is equal to 0. Now, we want to obtain the other pair of Maxwell's equations. Remember a relation that we found in tensor calculus for the divergence. Let me write it down. We found this relation A alpha equal to 1 over square root of minus g derivative with respect to x beta of square root of minus g A alpha beta. So this is the divergence of A alpha beta, the covariant divergence in particular. So let's first define f mu nu like this with upper indices. This is just a simple calculation. We have to calculate g mu alpha times g nu beta times f alpha beta. And also we define the contravariant vector j mu, which we will discover to be the density of the electric current. According to this equation here, we can form the equation. Let me write it down like this. We have j mu on the left, which represents this vector here, equal to, now we have to write this, but also remember that the square root of minus g is equal to 1 in our frame of reference. So we have derivative of f mu nu with respect to x nu, where f mu nu with upper indices, of course, is defined like this, as we know from the rules of tensor calculus. Now let j mu be written like this. If we use coordinates, we have jx, jy, jz, which is the three-dimensional current density in particular. And then here we have the density rho. Also, in the case of special relativity, f mu nu with upper indices can be calculated from f alpha beta with lower indices as previously defined. So here, a simple calculation yields, so we are assuming now that we can write our equations in special relativity. So g mu alpha, g nu beta have a very simple form. They are diagonal matrices, and we know the form of these matrices. So in this case, f23 is equal to hx, f31 with upper indices is hy, f12 is equal to hz, and also f14 with upper indices is equal to minus ex, f24 is equal to minus ey, f34 is equal to minus ez, and now if you insert these values here, these formulas, this one and this one here, we find, it's easy to see that this will yield these two equations: derivative of the electric field with respect to time plus j equal to curl of h, and then we have the divergence of the electric field equal to rho. So you can see that we have found the other pair of Maxwell's equations. Now we want to find also the energy components of the electromagnetic field. So I will start from this expression. We will form the tensor k sigma equal to f sigma mu times j mu. By considering the definition of f sigma mu in terms of the components of the electric and the magnetic field, we have k1 equal to f12 j2 plus f13 j3 plus f14 j4, which is equal to, if you substitute, hz j2 minus hy j3 plus rho times ex. And this expression here, these first two terms, give me the expression vector j, the three-dimensional current j, current density, cross h, the three-dimensional vector h, which is the magnetic field, and in particular we take the x component of this. You can do something similar for k2 and k3, whereas k4 has a slightly different expression. In particular, let me write it down. k2, you can find that this is equal to j cross h, the y component of this, plus rho times ey. k3 is equal to j cross h, and in particular the z component of this, plus rho times ez. Whereas k4, if you substitute and do a simple calculation, this gives you minus the vector, the electric field vector, dot product with the current density j. So k1, k2, and k3, as you can see from the formula, are related to the Lorentz external forces per unit volume. This is a simple observation. Whereas k4 here is related to the work performed by external forces. So if there are no external forces, we know that k sigma should be 0. In order to obtain the energy component, which is represented by T nu sigma of the electromagnetic field, we need to give to the equation that we wrote here, k sigma equal to f sigma mu j mu, a different form. And in particular, we should give it the form of an equation that we derived in previous videos. The form is this one. We have the derivative of T alpha sigma with respect to x alpha plus 1/2 derivative g mu nu with respect to x sigma t mu nu with lower indices equal to 0, like this. Now let's start doing our considerations. We have k sigma equal to f sigma mu j mu, and we also know that j mu, according to one of Maxwell's equations written in covariant form, this is the derivative of f mu nu with respect to x nu. And therefore we can rewrite this expression as derivative with respect to x nu of f sigma mu f mu nu minus f mu nu derivative of f sigma mu with respect to x nu. Let me write this index more clearly. This is mu. Now, let's consider this term here. So we will try to do some manipulations of this term. This can be rewritten like this: f mu nu times. Now, we know that we can rewrite also this expression like this. We have an equation like this: derivative f sigma mu with respect to x nu plus all the other permutations, which are df nu sigma with respect to x mu plus derivative of f mu nu with respect to x sigma equal to 0. Now, if we use this equation, we can rewrite this term like this. I'm going to do it here. F mu nu times minus derivative of f nu sigma with respect to x mu minus derivative of f mu nu with respect to x sigma, and this is equal to this term here that I'm going to rewrite here for the sake of convenience: f mu nu derivative of f sigma mu with respect to x nu. Now, from this equation here, we can also find this expression. We can simply rewrite it like this. We have minus f mu nu times derivative of f nu sigma with respect to x mu. Then we have minus f mu nu with respect to f sigma mu with respect to x nu equal to f mu nu derivative of f mu nu with respect to x sigma. So I have put this term multiplied by this term on the right, whereas this term here I have put on the left. Now, since this term here is equal to f nu mu derivative of f sigma nu with respect to x mu, and this is simply because f nu sigma is equal to minus f sigma nu, but f mu nu is equal to minus f nu mu. So the two minus signs cancel, and I can write it like this. Therefore, from here we find this. We find simply that f mu nu derivative of f sigma mu with respect to x nu is equal to minus 1/2 f mu nu with upper indices derivative of f mu nu with respect to x sigma. And now I'm going to rewrite it from here. This is also equal to, this is minus 1/2 g mu alpha g nu beta times f alpha beta times the derivative of f mu nu with respect to x sigma. And this can be rewritten like this for reasons of symmetry. It's easy to observe that this can be written as minus 1/4 g mu alpha g nu beta f alpha beta derivative of f mu nu with respect to x sigma plus g mu alpha g nu beta derivative of f alpha beta with respect to x sigma times f mu nu, and this is equal to, let me go below, equal to minus 1/4 derivative with respect to x sigma of G mu alpha, G nu beta, F alpha beta, F mu nu plus 1 over 4 F alpha beta, F mu nu, derivative with respect to x sigma of G mu alpha, G nu beta. And now I'm going to rewrite this term here. So let me do it below. This can be rewritten as a sum of two terms. When we differentiate with respect to x sigma, we have 1 over 4 F alpha beta, F mu nu, derivative of G mu alpha with respect to x sigma times G nu beta plus 1 over 4 F alpha beta, F mu nu, G mu alpha, derivative of G nu beta with respect to x sigma. And this is equal to, for reasons of symmetry, it's 1/2 F alpha beta, F mu nu, G mu alpha, derivative of G nu beta with respect to x sigma. So let me try to write this index mu a little bit more properly. Maybe it's clear, it's more clear maybe like this, but I hope you understand my handwriting. And this is equal to 1/2, and I'm going to rewrite the expression like this. F alpha beta remains F alpha beta, but I'm going to rewrite F mu nu here. I'm going to rewrite it like this: G gamma mu times G delta nu times F gamma delta times G mu alpha times the derivative of, do it here, derivative of G nu beta with respect to x sigma, like this. So I've simply written F mu nu like this, and you can see that those expressions are of course the same. Now we can put this one together with this one. So we can multiply those two together. And when we multiply those two together, it's easy to see, since G delta nu times G nu beta is equal to the Kronecker delta beta delta. So please do not get confused with these two deltas. This one here is the Kronecker delta, whereas this delta here represents the index. Now, for this property, you can easily see that when we multiply G delta nu by derivative with respect to x sigma of G nu beta, we can rewrite that expression as minus G nu beta derivative of G delta nu with respect to x sigma. And also we can put G gamma mu here together with G mu alpha, and when we multiply these two together we get the Kronecker delta alpha gamma, right? So this expression will be equal to minus 1/2 F alpha beta F gamma delta Kronecker delta alpha gamma G nu beta derivative of G delta nu with respect to x sigma, and this is also equal to minus 1/2 F gamma beta F gamma delta G nu beta derivative of G delta nu with respect to x sigma. And if you want, we can also relabel the indices differently. This is also equal to minus 1/2 f alpha tau times f alpha nu times g mu tau times derivative of g nu mu with respect to x sigma. Anyway, from here, from all these calculations, we can rewrite k sigma. Remember where we started. We started from k sigma here, and we did some manipulations here, and all the calculations are done here. You can see that we did some good amount of manipulations, but all in all, if you put these things together, you get this. So k sigma can be written like this. It is derivative with respect to x nu of f sigma mu times f mu nu plus 1 over 4 derivative with respect to x sigma of f mu nu times f mu nu with upper indices plus 1/2 f alpha tau times f alpha nu times g mu tau derivative of g nu mu with respect to x sigma. Now let's rewrite k sigma like this. So we can also rewrite this right hand side in this fashion. Derivative with respect to x nu of minus f sigma mu times f nu mu, and now you can see that I have put a minus sign here because I have changed the order of these two indices. Mu and nu become nu mu here, plus 1 over 4 delta nu sigma times f alpha beta times f alpha beta, and then I have plus, let me go below here, minus 1/2 g tau mu derivative of g mu nu with respect to x sigma, which multiplies minus f alpha tau, or actually I can also rewrite it like this, f tau alpha times f nu alpha. I have rewritten this term here by changing the order of these two indices and these two indices. So I will get two minus signs that will get cancelled. So this minus sign will get cancelled with this, and because of course this minus with this minus will give me a plus. So I didn't change any sign here. It's just convenient, as you will see shortly, to rewrite it like this. And in principle here I should close the bracket like this, but I'm going to add one more term, and you will see that this term will give no contribution. So let me first write down the term. It will be very similar to this one. The term will be this one. We have 1 over 4 delta nu tau f alpha beta times f alpha beta. Now, why does this term here give no contribution? Well, it's simply because when we multiply delta nu tau by what's outside of this parenthesis here, you will get this. You will get delta nu tau g tau mu derivative of g mu nu with respect to x sigma. Now, this is also of course equal to g tau nu derivative of g mu nu with respect to x sigma, but this will be 0 simply because this is proportional to the derivative of the square root of minus g with respect to x sigma. But we know that in our frame of reference, for our choice of coordinates, the square root of minus g is equal to 1. It is a constant, so this will be 0. Therefore, now I can define a quantity here, which I can call T nu sigma. And of course, we have a similar quantity here, but in this case, this is T nu tau, which is called the energy momentum tensor of the electromagnetic field. And with this definition, we have K sigma written like this. K sigma, let me try to write it down more clearly. K sigma equal to derivative of T nu sigma with respect to x nu plus, actually minus, here I have a minus 1/2 g tau mu, derivative of g mu nu with respect to x sigma times T nu tau, where T nu sigma, as I said, can be written like this. It is minus f sigma mu times f nu mu plus 1/4 delta nu sigma f alpha beta times f alpha beta. And this term here can also be written in a different manner. It can be written like this. It's plus 1/2 g mu nu with lower indices, derivative of g tau mu with respect to x sigma. Let me write mu here a little bit more clearly. And therefore, if we have no external forces, K sigma is equal to 0, and we get dt nu sigma with respect to x nu plus 1/2 derivative of g tau mu with respect to x sigma, and if we multiply g mu nu by t nu tau like this, we get t mu tau with lower indices equal to 0. And this is exactly an expression which we have already found. Therefore, in this case, T nu sigma here represents exactly the energy momentum tensor of the electromagnetic field. And we know that it must be the energy momentum tensor because we found also this expression, which must be satisfied in a general manner by the energy momentum tensor. It's an expression that we have already found, as I said in previous videos.